So eddy current tester testing, there's a picture of the eddy current testers that we'll be using. These are from a company called Z-Tech. You'll see a lot of our equipment. They're one of the big manufacturers of it, but this unit is a MIZ-21B. It's about a 10-year-old tester. They've kind of come up with some newer, more capable stuff that can do more 3D type modeling. But for basic eddy current testing, it does everything that even the newer ones do, unless you're doing like a 3D scan. Certainly better than our old one. We do have something called a MIZ-22, which was one of their ones they built back in like the 1980s. If anyone wants to try that one, I've got that as well. It's kind of on its last legs, but you can give it a try. In fact, some students like it because it's simpler. It doesn't have as many settings on it. So it's sometimes a little easier to set up. But that's what the tester looks like. What it doesn't show here would be the probes and other equipment that hooks up to it. But let's look at what eddy current testing is, and we'll discuss the process at a high level. And then as we move on in the lab, you'll get the opportunity to actually perform the test. So eddy current testing can have several uses. Probably the most common is crack detection. This is what's used typically for things like fuselage inspections to look for rivets that are starting to crack. This was that Aloha Airlines airplane where the top came off, part of the fuselage tore away. And so we do these kind of inspections in order to try to find that. We also use it pretty extensively on internal engine components for turbine engines. And again, looking for cracking. So things like fan blades. A few years ago, there was Southwest Airlines had a plane where they had an uncontained fan failure. Unfortunately, there was one passenger killed when that chunk of fan blade came up out of the front of the engine, hit a window, and she was pulled through that window in the vacuum. But this eddy current testing is what's used to try to find that before something like that happens. And in that case, they'd been doing the proper eddy current tests. It's the fan blade actually cracked in a location where they had not been, there was never a directive to inspect that area. And so cracks had formed in an area that was new. That engine, the CFM56, has had a whole host of problems with fan blade cracking. And there have been a lot of special eddy current test applications developed specifically for those engines. It seems like each new model, they've had some different forms of fan blade failure. This is also the type of failure that occurred for a Sioux City, Iowa crash. It was a DC-10. I want to say it was United Airlines, but I could be wrong. But they had an uncontained fan failure in the center engine, severed the hydraulic lines, and they flew the plane using differential thrust. Almost landed it. Unfortunately, when they got I think it was about 30 to 50 feet off the ground, the plane rolled over as they were in the process of landing. About half the passengers and the crew survived. There were casualties that did occur. So these types of tests are to try to avoid those kind of accidents. The other thing that this can detect is corrosion. So crack detection, we can find surface and shallow subsurface up to about approximately a half an inch deep. And so that's where the corrosion type of thing can take place, is that we can measure the thickness of a material. And so a particular area in aerospace where you'll see this, and you'll get to do this in lab, is if you have a lap splice. You have two pieces of metal that are riveted one on top of the other. We all know that that area between the two pieces of sheet metal is prone to corrosion buildup. Well, as that area corrodes, those materials, it's going to eat into the materials. It's going to make them thinner. And so you can detect that without having to pull that lap splice apart, take the rivets out, and actually see that. So that's the other area where corrosion, that this is used in aviation heavily. Some other things that it can be used for, more on the manufacturing side, material and coating thickness measurement, things like paint, chrome, chrome plating, different claddings and stuff like that. And so it can detect paint thicknesses down to the thousandth of an inch range. So if you're trying to get a consistent paint, particularly, you can actually detect within 1,000th of an inch paint thickness differences. Different material identification, so material sorting, things like conductivity. And then because it can measure differences in material as you go deeper, heat treatment and heat treatment depth monitoring, again, to make sure the part's been heat treated properly, where you have a thick enough wear layer, but you haven't heat treated it so much that you lose that strength from the non-heat treated core of the material. So advantages of this are it's sensitive to very, very small cracks and other defects. This can find cracks that are almost too small to find with like liquid penetrant, okay? And then it can detect the surface and near surface versus, liquid penetrant is probably the biggest competitor to eddy current testing, but liquid penetrant can't find anything subsurface. So if we're looking for not just surface but subsurface, this is a method we can use for that shallow subsurface down to that half an inch or so. Results are immediate. There's no like dwell times or developing, anything like that. The unit that you saw pictured earlier is portable. You can hold that in one hand, or you can wear like a neck strap and hold it while you use the probe with your other hand. So that one unit is about the size of a tablet. So it's not that big. It's fairly lightweight. It can be used for more than flaw detection, like I said, things like material sorting and whatnot. There's minimal part preparation. You don't have to remove paint, for instance. That's why we use it on the outside of the fuselage. You don't have to remove the paint in order to do those rivet inspections. So again, it's got that advantage over liquid penetrant, in that you don't have to strip the paint prior to performing the method. So it's a good in-service method of crack detection. And your test probe does not even need to contact the part. In some cases, this is done in a non-contact. Aviation, most of the time we're doing a contact type system. We're putting the probe directly up against the surface. However, if you think about it, it's technically a non-contact, as we're not actually contacting the surface we're testing, we're contacting the surface of paint. And there's actually a little gap between the face of the probe and the metal underneath, the thickness of the paint, where we're not really worried about what's going on with the paint. Paint cracks, you can see, not as critical. The other part of it, compared to magnetic particle, is that this can be performed on non-ferrous parts. So we use it a lot for aluminum, the fuselage and that kind of thing. Titanium parts, like you have in your engine, and then your high carbon steel, like stainless steel and that kind of thing. Chromium steel, stainless steel, chromium steel, that are less, are hard to magnetize. And so we can use this here. It does have some limitations though. So the material must be conductive, which by conductive I mean electrically conductive. And so it's not a technique we can use for composite materials. It's limited. Again, like I said, it's often used for aluminum, titanium, those chromium and high carbon steels. It can be used on normal steels as well. It can be used on magnetic. It can be used on ferromagnetic materials, but it can be used also on non-ferromagnetic materials. Though we don't have to have contact with the surface, we have to be able to put the probe directly in line with the surface. So we can't have something in between whatever it is we're inspecting and the face of the probe. The advantage there, we really haven't had anything where you could do this, right? Surface must be accessible. Surface has to be accessible for dye penetrant. Surface has to be accessible for mag particles. Surface has to be accessible for borescope, where you can see it. Anyone know what a method that may not require the surface to be accessible would be? We haven't talked about it yet, but any ideas? What can see through materials? Yeah. A lot of you have probably had one of these. You go to the dentist, you get them. What's that? X-ray. So, that's where it has a limitation. X-ray can be used in a place where you're not able to necessarily access the surface. So this has to have direct access, though it doesn't have to necessarily touch it. It does require a certain amount of skill and training. Again, I mentioned before we started that it is, you're running a probe over a part, and it's producing an indication on a screen, and you have to be able to interpret that indication. So now you're getting indications on a screen, and you have to be able to decide, is that indication a relevant flaw? Is it a non-relevant indication because of some geometry or material in the part, right? Or is it a false indication because of a process error? And so before we start, we actually we have a calibration block we're going to use, and you actually get, you look at what those different indications would look like, so that when you go actually test the part, you can have some idea or be able to recognize whether you have a relevant, a non-relevant, or a false indication. Surface finish and roughness can interfere. When you're doing this, you're going to do, particularly when we're doing corrosion inspection, our probe likes to kind of catch the surface. It's a bigger probe that has a lot more friction, causes it to wobble. That wobble causes false indications. So, surface roughness can cause issues with it, because what it's doing is it's sensing a change in the amount of metal in front of the probe face. So when you have a rough part, some areas are going to have a little bit more metal, right? Some areas are going to be like a dip between two rough points, and there'll be a little bit less metal. And so it's going to cause a little bit of a non-relevant indication on your screen as you move across that area. I mentioned the reference standard. We need to have a standard that matches our part, or that is designed to be able to provide a reference against whatever part it is we're going to be testing. So you can't just grab it and go test whatever you want, because you have to have something to compare your results against to know if your results are accurate. Versus you can just grab dye penetrant cans and go out and look for cracks. You can put a part into the mag particle machine and look for cracks. You can get a borescope and look around at it. In this case, you have to get a standard that matches or simulates what it is you're looking at. Some things, sheet metal, that's pretty easy. There's kind of standards for sheet metal. You can use it on this piece of sheet metal and this piece of sheet metal and another piece of sheet metal. But one that's specific, these are used oftentimes to check wheel rims for cracking, the bead seat where the bead goes for the tire. And if you're doing that, you have to actually have a standard that essentially is a piece of that same casting or forging that has had artificial flaws put in it in order to be able to see what those expected flaws look like. The last part, depth of penetration is limited, as I mentioned previously. An advantage is it can find shallow subsurface. The disadvantage is it can only find shallow subsurface. You can't get more than about a half an inch deep into a part in order to find those. So eddy current testing relies on, at its fundamental level, it relies on electromagnetic induction. I'm going to pull this video up here in just a second. But what that means, because it is dealing with electromagnetic induction, the piece has to be electrically conductive. In order to build a magnetic field, an electromagnetic field in it, current has to be able to flow through it. And so, again, that test piece doesn't have to be ferromagnetic, aluminum, titanium, but it does have to be conductive. And then it's comparative. We have to have that reference standard. So. So we've got our bar magnet sitting there. It's stationary, and it is, you can see our galvanometer is reading 0. But if we grab our magnet and we move it, you can see we get a magnetic field. I can move it through this coil, right? And if I move it one direction, I get a positive current. If I move it the opposite direction, I get a negative current. So right now, if I move it to the right, I get a positive current. Move it to the left, I get a negative. I can make my magnet stronger, or I can make the coil bigger so it'll capture, it'll be affected by a larger portion of the magnetic field or flux. And now you can see if I move it, I get a bigger deflection. So when I move it to the right, it's positive. If I flip my magnet, now when I move it to the right, it's negative. Now I go positive. So the direction of the field and the strength of the field and how quickly I move it, the faster I move it, the bigger the current, or the bigger the voltage induced. We can induce a current. So the way our eddy current testers work is, the first part of it is we need to induce a magnetic field by with an electromagnet. So we run current through a coil, that creates a magnetic field inside our probe. That field touches our part, goes into our part, and it induces a current and ultimately a magnetic field inside of our part. Okay, so it can go both directions. An the magnet moving through a coil can induce a voltage going through the coil can induce a magnetic field, an electromagnet. Okay? So what we're going to do is we're going to use that field. We're going to induce a magnetic field in our part, and then a second sensor, a second coil of wire inside of our probe, or depending on the probe, some use one coil, but typically a second coil of wire inside our probe. That is going to sense the magnetic field produced by the part from the magnetic field that is going into the part and inducing what are called eddy currents in it. And when the metal changes, when the part changes, something about the part changes, it's going to change the magnetic field that is being sent to that pickup coil. And our tester is going to be able to sense that. Okay? So here's our section on our video on eddy currents. The videos we just looked at showed a constant magnetic field. They were a magnet where it's always, the field's the same direction, right? A bar magnet or that kind of thing is always going to have a field the same direction. But what we're going to do is we need to have a changing magnetic field. And so the way we can do that is by running an AC current through our coil. We'll get a field that builds one direction, collapses, builds the opposite direction, collapses, builds one direction, right? So it's going back and forth. So it's a constantly changing magnetic field, which will induce a current in whatever object, whatever conductive object we put here. And then that field hitting that object is going to cause a current, what's called an eddy current, a little circular current to form in that conductive material. And then those eddy currents are going to have their own little magnetic fields, and we're going to sense that. And whenever the material changes, whether it's thickness or a crack or something of that nature, we're going to be able to detect those changes. And so if we're going across a piece of sheet metal, it should be fairly consistent, right? But if we cross a crack, we'll get a change. And we pick that up. If we are going across a piece of sheet metal that's a certain thickness, and all of a sudden it gets thinner because the backside of it's corroded, it'll change the strength of those eddy currents and the resulting little magnetic fields they produce, and we'll be able to sense that with our tester to tell us that there's a corrosion issue there. So there are some properties that we have to be aware of with inductive circuits. So some of the properties of inductive circuits that we have to keep in mind. So inductance is the first thing, is a current carrying coil. When we run a current through it, it's going to produce that magnetic field. Right? If we run a DC current, that magnetic field will rise to a certain level and it'll stay there, certain level, certain direction. And that's fine, except in order to induce current, we need a constantly changing magnetic field. So that's where we're going to use an AC current instead of DC. Right? But if you're running DC, you'll get that magnetic field and it'll stay there. If you're using AC, it'll be a constantly building and collapsing, building the opposite direction and collapsing, building back the original direction and collapsing. And so this is given by, inductance is measured in henries, and the symbol for a henry is, you'll see, is an L. The next one is inductive reactance. And that is, now, this is when I talked about that field is going to induce a current in the part. And then that current in the part's going to have its own magnetic field. That magnetic field will then go back and react with the same coil. Okay? So earlier I said you can have a what's called a driver, which is your source of magnetic field, and a separate pickup coil. There are versions where it just uses one coil, where it's a driver pickup. The single coil does both. Because what's going to happen is this inductive reactance is the eddy currents that form in the part and the magnetic fields they produce when you're running an AC current, when you're driving this with an AC current, they're going to be out of phase. So the current, those magnetic fields are then going to try to induce a current back in the coil. And the current they're going to induce in the coil is not going to match up with the current we're sending to the coil initially. And when you get two AC currents like that, they're going to pull each other different directions. Can I reach? Almost. So if we look at it, if we draw a sine wave, I think I can just barely get to the board here. If we have, here is our voltage, right? And this is time, over time on the x-axis. So if we put a current into our part, it's going to look into our coil, excuse me. We're going to put a current into the coil. That's going to induce a magnetic field. That magnetic field is going to interact with our metal part. It's going to form eddy currents, little circular currents in our part. And then those currents are going to have their own magnetic field that are going to go back to the coil. The thing with those currents is they're going to be about 90 degrees off. They are going to be 90 degrees off from our current. So they're going to peak right here. And then they're going to come down here and peak right here. Okay? So what that means is when these currents add together, what the tester is going to feel is the sum of these two. So at this point, what the tester is going to notice is going to look something like this. It's going to be about halfway between. It's going to peak right here, and then it's going to stay halfway between here. So this is our original current that the tester's sending. This is the current and the magnetic field from the eddy currents. And so it's going to kind of drag back or drag over the resultant frequency in the coil. And so our tester can pick that up, and that's what it's sensing. And if there's a change in metal, the amount, how high this wave is right here, the amplitude of it, of the induced wave, is going to change. Because the more metal, the stronger it's going to be. You go to a thinner part or a cracked part, there's going to be less metal in front of the probe, so it's not going to cause as big of an induced current. And so ultimately, this resultant blue wave is going to change anytime we go over some kind of flaw or a change in the material. So this is given by a unit ohm, but it's not the same type of ohm. It's not a straight resistance like you're used to, right? A resistor just impedes the flow of current. This is causing a change in current because of those magnetic fields. Okay? And it's known as inductive reactance. But instead of using the little omega symbol, it uses the symbol X sub L. It's inductive reactance. And what ultimately happens then is not only the coil will have this interaction. Now a coil is a length of wire, so it's going to have a certain amount of normal resistance. And so when you add these together, the inductive reactance, which is the resistance from magnetism, plus the resistance in the coil, just the nature of it being a wire and having a certain amount of resistance, you're going to get what's known as impedance. Except, remember, this one is 90 degrees out of phase. The inductive reactance is 90 degrees out of phase. The standard resistance of the coil is in phase. It's just going to make the amplitude of this primary wave, the solid line here, smaller. So that doesn't really change. The actual resistance of the coil of the wire that makes up the coil is not going to change. That's fixed. But the inductive reactance is going to change as the amount of material in front of the coil changes. Okay, how much inductance you get from the material changes. And so what we're going to see ultimately on our screen is this impedance right here. That's what our tester is going to measure. That's also given the unit ohm, just to make it more confusing. So we've got straight resistance as an ohm. We've got inductive reactance is also called an ohm. And we've got impedance is also called an ohm. But the symbols are different. So this uses a symbol Z. So the ohm uses the omega, the standard resistance ohm. Inductive reactance is X sub L, and ultimately impedance is Z. And we are going to be looking at the impedance of our probe to know if something's changing in front of it. And that's what our tester is going to look at. So this is kind of an illustration of what I explained. So in a resistive circuit, current and voltage are in phase. Okay, the resistance is just going to reduce the amplitude of the sine wave of the current running through the coil. In an inductive circuit, because it's 90 degrees out of phase, the current's going to lag the voltage by 90 degrees. That's what this dashed black line is I drew here. And so you add them together. So this is a resistive circuit. So if you didn't have any resistance, this would be the larger line. It's I sub G. Current sub G. And then voltage with resistance, you can see I brought that down. Here's that inductive circuit like I've got here. And so you add those together to get the impedance. So that total resistance. And that's where the vector sum comes from, because you're not just adding the total amount, you're adding because this is AC, it's got a direction as well. The phase is offset. Okay? So on our screen, the way it's displayed by our tester is that resistance is one direction. Now this shows resistance on the x-axis, inductive reactance on the y. They're 90 degrees apart. With our tester, we can rotate this any direction we want. Okay? And so we typically are going to rotate it so that our indications go a certain direction, depending on what kind of an indication we're looking for. For most cracks, we put our origin at the lower right-hand corner, and we have the cracks go up and to the left. When we're doing corrosion, we kind of put it in the center of the screen that makes kind of a little bow tie or flower-looking symbol. So just keep in mind that, even though this says resistance here, phase, we can take this whole view and we can rotate it any direction we want. So you'll see, I mentioned that inductive reactance, resistance tends to be fixed, inductive reactance will change. Right? If that was the case, it would always just move up and down along this line. But we can rotate this any direction we want. That's one of the things when you do your report is you will note your phase angle, which is the rotation of the screen. So if we look at it on the tester, it looks like this. So here's a screenshot of that, and this is 3 different cracks. Like I said, we start with the lower left or lower right corner, and typically when we show cracks, we have them go up and to the left. So we plot the resistance vector and the inductive reactance vector. And as I mentioned, it's not necessarily tied to a given axis. The screen is rotated, can be rotated. And that changing impedance, that changing vector sums, gives us this. So what happens is this is a graph over time. So when we first put our probe against our part, we clear the screen, and it almost looks like a little Etch-a-Sketch. If you don't touch the knobs on Etch-a-Sketch, what happens to the little pointer, the little drawing thing on it? Everyone's used an Etch-a-Sketch, right? Just the dials, huh? Like the one in Toy Story? Yeah, or a real life one? Yeah. I know they still sell them. My kids have one, so it's not like they stopped selling them. they were a lot better back then. They were like heavy duty. The new ones are really cheap. They put toxic stuff in them. They probably were lead or something at one point. So it's almost like that. Like you can imagine, it's like one of those etch-a-set screens. We set our origin right here, and as long as we keep our part, our probe against the part in one location, there's no change going on, right? We have a consistent amount of metal in front of that coil, which means we're going to have a consistent amount of impedance and inductive reactance in the coil. So that point doesn't move. And if we start to slide our probe across the surface of the part, as long as nothing changes about the part, as long as the thickness doesn't change, as long as we don't go across a crack or a flaw, as long as the geometry doesn't change, that impedance and inductive reactance aren't going to change. And so that point will stay at its origin down here in the, wherever we set it. We can set it where we want, but typically with cracks, we put it in the lower right corner. But as we go along, if I go across a crack, it causes that inductive reactance and impedance to change. And as it changes, that point moves. And so again, this is graphing that point's position over time. So it draws lines as you continue to move your part. If you stop at any point, that's where the point stays. But as you continue to move, it'll continue to move. And what you get is the size of the flaw is related to the size of the indication. So you have, this is showing 3 different flaws. The smallest flaw is this bottom line in the right. Then we've got kind of a medium-sized flaw that goes up to roughly the middle of the screen. And then we've got the largest flaw goes almost to the top left corner. And we can adjust how zoomed in we are or how zoomed out, because different materials and different flaws are going to have bigger or smaller indications. And so we can make adjustments to compensate for how sensitive we need to make our probe. We can adjust how much power we're sending in the probe, which will play a part in how strong those eddy currents are and how strong the induced magnetic field is. We can adjust the sensitivity of the pickup coil, whether it's the same coil or a second coil. We can adjust what's called the gain on that. That's how sensitive it is. You may have heard that in terms of like microphones, how sensitive a microphone is. This is kind of the same thing, but just with electromagnetism. So how closely are we listening for those changes? And then we can adjust how zoomed in or out we are on the screen. We can even adjust the scale. Do we want to spread it taller but not wider? We can change the aspect ratio in order to get an indication that's easier to see. And so we'll be looking for indications that look something like this. So I'm going to go ahead and stop there.